So this is the boron source, boron oxide, but it's not straight boron oxide because boron oxide melts at 500 Celsius or somewhere on there. So we're going to be running it at today 1100. So this is actually a glass, a ceramic that consists of aluminum oxide, magnesium oxide, and embedded inside is some boron oxide. So basically, when it gets hot, the boron oxide that is embedded in this disc will start coming out, vaporizing and depositing on the surface to produce our dopant source, which gets driven into the silicon. Here is the structure. We got the boron oxide in the middle, or the ceramic that contains the boron oxide in the middle, silicon on either side. The doping side is facing the boron, and this is the back side, which we are not doping, but we will have to dope that too later because that's an N-type substrate. We're going to run this at atmospheric pressure, but not with air. I'm going to replace it with nitrogen because we don't want to oxidize the silicon. So before I do that, I have to put the baffles. So these are insulator blocks, one on that side, so that prevents excessive heat from flowing to the output. All right, so we put the temperature baffles, and here is the wafer. We move it to the center of the furnace, so approximately at the center, and then more thermal baffles on the other side. All right, so there's heaters on the bottom and heaters on the top, and there's a thermocouple here that's touching the glass, and that's what's measuring the temperature. So there's the nitrogen flow on the leftmost tube. There's a little ball that floats. I just want to flow as much nitrogen as possible. I'll go to full scale. And the sensor, there's an oxygen sensor over here. So basically, the nitrogen is flowing through here, through the tube, and on the exhaust side, that's measuring how much oxygen is leaving the furnace. So I want to bring it down to 1% oxygen, and then I'll turn on a slow flow to maintain 1%. And that 1%, the purpose of that is to slightly oxidize the surface so that we don't excessively dope the silicon, because too much boron in the silicon forms another compound, silicon borate, which is very difficult to remove. So this oxygen will oxidize the excess boron and keep it from forming that silicon borate. So ramp it up to 1100, hold it for 20 minutes, and then keep holding it for another 15 minutes while we switch the gases from nitrogen to 100% oxygen. The purpose of that is, again, to remove that excess boron on the surface by oxidizing the silicon, turning into borosilicate. So it's SiO2 with boron in it, and that could be etched off when we remove the etch. So we don't want, that's one of the drawbacks of this thermal diffusion doping, is excess boron on the surface that causes some problems on the surface, precipitation of boron and all that. You don't get that with implant. So I think this is about it. It's going to run, it's going to take 2 hours for it to get up to 1100, and then it's going to only wait for half an hour, and then it cools down, and it's going to take overnight to cool down. The cooling down is very long. It's going to be hot. We don't want to open it, so it'll be tomorrow, or tomorrow's Thursday, so probably sometime on Friday or weekend I'll come and take it out, and then we'll remove the excess boron that is on the surface, etch away in BOE, buffered oxide etch, and also remove the PECVD oxide. We don't need that anymore, so we can take it all off. And then what I'm going to do after that is I'm going to flip the wafer, dope the backside, so I have a phosphorus oxide source, use that, dope the backside. So be done with the high temperature processes early. You don't want to introduce high temperature processes after you do metallization, because the metals will diffuse if you introduce them to high temperature. So you want to do both doping steps right now. So that's going to be the next couple of steps.